Okay, so this is going to be our first video from chapter 17, where we're looking at equilibrium. If you don't have a printer at home, you can easily take notes on a sheet of paper. If you can download these and go straight to them, that's good as well. So keep in mind, I'm at home. You might hear my kids in the background, my dog's in the background. Bear with me on the noise. So chapter 17, we're going to go through a couple of the sections here. Do as many of the videos as you can, and then we'll throw some practice problems in. You guys are going to like this unit because it's pretty straightforward. So equilibrium. Basic concepts. Reversible reactions do not go to completion. So originally until now, you typically have seen an A plus B with a single arrow going to C plus D. And in this type of reaction, it's assuming that all of A and B fully react stoichiometrically and produce products, and then the reaction stops there. For reversible reactions, you notice reversible reactions by the double arrow. They can occur in either direction, meaning our reactants form products, and then while those products are forming, they interact with each other and turn back around and form more reactants. And so symbolically, this is represented as the reaction that you see here. Okay. Chemical equilibrium exists in two opposing reactions that occur simultaneously at the same rate. And so what we can do is we can say that the rate of the forward reaction, okay, is equal to some constant, the forward constant, A times B. Now remember, these have to be experimentally determined, okay? But this represents the forward reaction rate. It also, we have the rate of the reverse, okay? And at equilibrium, these two are equal to each other. And we can substitute and set these two equations equal to each other. Okay, we'll get more to that here in a minute. So a chemical equilibrium is a reversible reaction that the forward reaction rate is equal to the reverse. Okay, and once again, we'll set these equal to each other here in a minute. Chemical equilibria are dynamic equilibria, which means that molecules are continually reacting, even though the overall composition of the reaction mixture does not change. Now, graphically, this is something that you'll just kind of want to pay attention to. This is a representation of the rates of the forward and the reverse. So if you think about the very, very beginning, the concentration of A and B is going to be really high. And as these decrease, okay, C and D are also forming. Well, at some point, these two are going to plateau. Okay, and you can see here A and B plateau, we go to that straight line, C and D form. And that means that equilibrium has been established. No more products are being produced while no more reactants are being consumed, okay, and vice versa. Okay, so one of the fundamental ideas of chemical equilibrium is that equilibrium can be established from either the forward or the reverse direction. Because we know C and D react, if we had started with those, we would have formed A and B, and vice versa. Okay, go to the next one. So let's talk about the equilibrium constant. Okay, for a simple one-step mechanism, reversible reactions such as this, okay, where A plus B yields C plus D and then turns around, same. The rates of the forward and the reverse reactions can be represented as what we drew above. So I'm just going to kind of copy those, and let's see if this works. Nope, that's going to butcher it. So let me just rewrite that. Okay, so we know that the rate of my forward reaction, and this is kind of picking up from kinetics in the last. Okay, we know the rate of my reverse, okay, can be represented as those two. And we know that at equilibrium, my rate of my forward is going to equal my rate of my reverse. So yeah, so we can take literally each of these portions and set them equal to each other, okay? Because the ratio of two constants is constant, we can define a new constant. So let's solve this, okay? Let's set these equal to each other and solve for our constants, okay? And so I'm just going to kind of take this, KF, we're going to say KR, that's the reverse. We're going to solve this for K's, okay? It doesn't matter what you move to what side. Okay, let's say that I'm going to move my K over, so I have KF divided by KR is equal to, C and D stay on the top over here, divided by AB. Okay, and what we can do is we can take this portion here and we can define a new constant. Okay, a new constant, which we're going to done here as KC, okay, and we know that KC, which is going to be our equilibrium constant, is equal to the concentration of C times the concentration of D over the concentration of A times the concentration of B, okay. Now, Kc is defined for a reversible reaction at a, and this is pretty important, given temperature, as the product of the equilibrium concentrations in molarity of the products, each raised to a power equal to its stoichiometric coefficient. So what you don't see here is, let's say that the front of this reaction each had a little subscript, right? Okay. Our equilibrium expression would also have those stoichiometric coefficients as exponents on each of these, okay? And so basically you have your products over your reactants. And this is going to be good for all valid reactions, okay? You can write this equilibrium expression for that. Okay, divided by the product, right here in the notes, of the equilibrium concentrations of the reactants, each raised to their power. Okay, so knowing that, oops, I didn't even do that. Let's go on to the next page, and we're going to work example 17.1a. I'm going to stop the video and start a new one. We're just going to practice this really straightforward.